Okay, so welcome back. So in this lecture, so I'll be describing about this hyperbolic metric spaces, and uh, so a glimpse of the definition already you have seen from the lecture of Professor Sri Krishna. So he also described this hyperbolic geometry, and so let me go through some bit of this hyperbolic geometry, definition of this hyperbolic plane, this upper half plane model and this model. And what I'll try to do, so I'll try to prove that these triangles are slim in this hyperbolic plane, and then I'll move to this general geodesic metric space. Uh, so when we call it to be hyperbolic metric space. So let us begin with this hyperbolic plane. And so if you have any question, you just stop me and ask. Yeah. So this already has been described. So we start with this upper half plane. So we start with this upper half plane, and yeah. So this also you can write as, so Z belongs to C, thus that the imaginary part of Z is greater than 0, and we equip this upper half plane with this Riemannian metric. Okay, so there's a different Riemannian metric. It is different from this Euclidean metric. So how it is defined? D squared is equal to dx squared plus dy squared by y squared. So another way you can express this metric, Riemannian metric, in terms of this complex numbers. So this is dz times dz part by imaginary part of z squared. Okay, where this z is equal to your x plus iy. Okay, so this definition already you have seen. So this metric, so this thing, so this Riemannian metric, so we'll call it to be the hyperbolic metric or Poincare metric. Okay, yeah. So now given a path in this upper half plane, and let us, so we know that this upper half plane, this has a differentiable structure, and so we can make sense of differentiable path, even piecewise differentiable path makes sense. And let us take gamma to be a piecewise differentiable path. And what do you mean by length of this path? Yeah. So gamma t, you can write it as this xt plus I yt. So length of this gamma, okay. So this is this integral. So this already it has been defined. So length of this gamma. So this is integration 0 to 1 root over dx dt whole square plus dy dt whole square by t dt. Okay. So this is the same thing as this integration. Okay. Okay. And now how do you describe this distance between these 2 points? So this also has been described by Sri Krishna. So you take 2 points, ZW belongs to the upper half plane. So the hyperbolic distance between Z and W. So this is defined to be the infimum of length of gamma. Okay, so where this infimum is taken over all piecewise differential paths joining Z and W. Okay, so you can check that this indeed, so this indeed it is a distance function, it is a metric on this upper half plane. Okay, all right. So, okay. So this you can check that this in fact it is a distance function on this upper half plane. So this I'm not going to. Okay. So yeah. So you already have the definition of this isometry. So a homeomorphism from T from H2 to H2 is said to be an isometry if T preserves the this line element. It means the T preserves this Riemannian metric. Okay, so T preserves this Riemannian metric. Okay, so corresponding to this Riemannian metric, so we'll get an inner product. So this T will preserve that inner product also. Okay, so this definition already you have seen. And what do you mean by this isometric group of this upper half plane? So you take the this set up all isometries of this upper half plane. So this will form a group under the composition of maps. Okay. Yeah. So next job is to show that this PSL to R. Okay. So this is the set of all. So first you take SL to R. So this numerator. So this is my SL to R, and you quotient it by plus minus identity. So that is my definition of this PSL to R. So this PSL to R, so in fact it is isomorphic to a subgroup of this isometry of this upper half plane. Okay, so again, yeah. So this in fact, this will be the set of group of all orientation preserving isometries of this upper half plane. Okay, yeah. So how do you do this thing? So first, you should have an action of this PSL to R on this upper half plane. So PSL to R is acting on, so PSL to R is acting on H2 in this way. This action is by Mobius transformation. Okay. So now if I take the Z, so I have taken the Z in H2. Okay. So this AZ plus B by CZ plus D, it will land in fact in H2, not it will be a general complex number. So it will be, in fact, it will lie in H2. Okay, so this is very simple to prove. So this I have proven here. So imaginary part of dz, this will be equal to this. So this is greater than 0. So therefore, d of z, it belongs to your upper half plane. Okay. Yeah. So this, therefore, we have an action of this PSL to R on this upper half plane. Any question? Yeah. Okay. Sorry. Okay. So in fact, one can prove that this map, so the, in fact, is a homeomorphism. And so therefore, this PSL to R, it acts on this upper half plane by homeomorphism. Yeah. And so this, all these maps, so this, in fact, so these are my isometries. Okay. Yeah. So this thing I have proven here. So theorem is this PSL to R is isomorphic to a subgroup of this isometry of this H2. Okay, so you just take this map from PSL to R to this homeomorphism group of this upper plane. Sorry. This thing. Yeah. So you take this map, okay, and one can prove that. So this Tz equals to Az by B by Cz plus D. So this in fact is an isometry of this upper half plane. Okay, so this computation I have done it here. So one way you can prove this to be an isometry. So if I take any path gamma, gamma is a differentiable, piecewise differentiable path in the upper half plane. Length of this T of gamma will be equal to length of gamma. Okay. Yeah. So gamma T, I have taken it to be xt plus I yt, and suppose Tz is u plus ib, so then T of gamma T, it will be of this form. Okay, so by definition, length of T of gamma is equal to this thing. And if you compute this one, so this will be, so this computation I'm not going in detail. So this will be equal to this thing, and one can check that. So one can check that this, yeah, so mod of this T prime gamma T will be again equal to this thing, and length of T of gamma is equal to your this one, which is exactly equal to the this length of gamma. Okay, so this will prove that this T is an isometry, and in fact, from this the definition of this distance function, so distance between Z and W, so this will be equal to your this H2 distance of Tz and Tw. Okay, so this are very standard proofs. So I'm not going into this thing. So what I'll do, I'll pass this note to you. We can check all this thing. Okay. So okay. So this part also has been said by Sri Krishna. Okay, so what are geodesics in this upper half plane? Okay, so he has said that the vertical lines and the semicircular are with center at real axis. So these are my geodesics. Okay, yeah. uh, Okay, so first of all, what is the definition of geodesic here? So a piecewise differentiable path gamma between z and w. So this is geodesic if length of gamma is exactly equal to the distance between z and w. Okay, so this gamma is the length minimizing path joining z and w. This is the definition of geodesic. Yeah. Okay. So I want to prove that the semicircle and straight lines are geodesic. Okay, so first job is to show that this vertical lines, so these are my geodesics. Okay, so how do I do this thing? Uh, so, so first you take any point on this imaginary axis. So, yeah, so I have taken these 2 points on the imaginary axis, and you take this. So you take any path joining this IA and IB. So this is my path gamma. So gamma t is xt plus iyt. And by definition, so length of gamma is equal to this thing. Okay. And now note that the numerator, okay, so numerator is always greater than equals to your mod of dy by dt. Okay. So therefore we have this inequality here. Okay, so this integral is greater than equals to this integral. Fine. And again, so we have a mod here. So this is again greater than equals to this thing. Okay, so this is basically your yeah. So integration a to b dy by y, which is equal to your log b by a. Okay, so gamma is a path joining IA and IB. So what we have found that length of gamma is greater than equals to log b by a. All right. Okay. And now if I take beta to be the, so if I take this beta t to be your, let us take this it. So t is varying from this a to b. So image of beta, so this will be a geodesic here. Okay. So of course I am not writing the parameterization here. So so length of this beta, so this will be equal to your log of b by a. Fine. So length of gamma is greater than equals to your beta. So maybe you can take this orientation. I don't know. So is this okay? Yeah. So I think this is better than the previous view. Okay. So what we have shown that length of gamma is greater than equals to log b by a, and if I take this beta t to be this thing, so instead of, do not take this. Yeah. So beta t is this thing. So image of beta, it lie in this imaginary axis. So length of beta, so you can compute it to be exactly equal to log b by a. So length of gamma is greater than equals to log. Sorry, length of gamma is less than greater than equals to length of beta. Okay, so this implies that so this beta is a geodesic between IA and IB. Any doubt? Fine. So what we have proved that, so if I take the upper half plane and let us take this imaginary axis. So this path beta. So this is a geodesic in the upper half plane with respect to the hyperbolic metric joining IA and B. Okay, all right. So now, how do you prove that the semicircles are geodesics? So now you take an isometry. So let us take T to be an isometry of this upper half plane. And this isometry, it takes geodesics to geodesic. Okay, so suppose beta is a geodesic, so then T of beta, so this will be also a geodesic. Okay, and now notice that, so this T, it is a, so TZ I have taken to be AZ plus B by CZ plus T. So, okay, so TZ I have taken to be AZ plus B by CZ plus T. And so this A, B, C, D, it belongs to your SL to R. So the speed is an isometry of this, this upper half plane. So T of beta, it will be geodesic, and T is also a Mobius transformation. Okay, so this T is so Mobius transformation. So it is, in fact, it is conformal, means that it preserves the angles. Okay, so it preserves the angle. Okay, so therefore what we have, so we already have proved that, so this imaginary axis, so this is a geodesic. Okay, so now if I apply T on this thing, okay, so image of this vertical line, so this will be either this, or again it will be a vertical line. Okay, so T is conformal, means that this angle will be preserved. Yeah, so when I say conformal, so then we are moving to complex analysis. Okay, so then yeah, so another thing is that, so TZ is equal to your AZ plus B by CZ plus D. Okay, so this T is defined from this upper half plane to upper half plane. Okay, so if I take Z to be real number also, so T of Z is, again, it is a real number. Okay, so you can extend this map to this. So you can extend this map to H2 union your heart. Okay, all right. Yeah, so one mistake I have made. So this, in fact, should be Z union your infinity. So T of Z, it belongs to your hard union infinity. Okay, so this, so T can be extended to your H2 union hard union infinity to this thing. Okay, yeah. So now you think in terms of complex analysis. So this angle will be preserved. Okay, so image of this this imaginary axis. So this will be either a vertical line, or it is a the semicircle. Okay, yeah. So therefore, so the semicircles and this vertical lines. So these are my geodesics. Yeah. So this part I have explained it here. Yeah. And another thing is that, so suppose we take 2 points. Suppose we take 2 points, Z1 and Z2 in upper plane. And so Z1, suppose Z1 and Z2, it does not lie on a vertical line. Okay. So then the problem is to find a semicircle passing through the Z1 and Z2. Okay. So given any 2 points in the upper half plane, why there exists always a geodesic passing through the Z1 and Z2. So you know that vertical lines and semicircles are geodesics, and suppose Z1 and Z2, it does not lie in the vertical line. So what will show that there exists a semicircular arc joining the Z1 and Z2. Okay, so how do I do this thing? So now you do this Euclidean, this basic this coordinate, what you call this to be not coordinate geometry, school geometry. Okay, so join this Z1 and Z2 by Euclidean line segment L, and let us take this M to be the this perpendicular bisector of this thing. Okay, this line L. So this will meet this real line at some point X. Okay, and now what you do, so you take this length, so this length, these two lengths, it will be equal, and draw a semicircle with center X and radius your just distance X. Okay, so this you can take to be the, yeah, so this is my Euclidean radius. This is same as this two. Okay, so we'll get a semicircle which will meet this real line orthogonal. Is it okay? Any question? Yeah, please feel free to ask question. Okay, so what we have shown that so given any 2 points in the upper half plane, there always exists a geodesic joining the Z1 and Z2, and in fact that geodesic that will be unique. Okay, so this comes from this computation. Okay, so this H2 with the hyperbolic matrix, so this is a unique geodesic matrix space. Okay, all right. Okay. So any question? Yeah, so then let us move to the next part. Okay. So Sri Krishna also mentioned about the this another model of this upper half plane. Okay. Okay. So what is so I'll be explaining about this model of this upper half plane. Yeah. So first, let us consider this Mobius transformation. T from C union infinity to C union infinity. So T of Z is equal to Z minus I by Z plus I. Okay. Yeah. So so one can check that. So one can check that if Z belongs to your upper half plane. Okay. So mod of Z minus I by Z plus I, it is less than 1. Okay. So this T, it is a Mobius transformation which takes this upper half plane to your this unit disk. Okay, so what is my D2? So this is my open unit disk. So T of this upper half plane is your this unit disk. All right. Okay. So now what I'll do? So I already have a this metric, this Riemannian metric on this upper half plane. I'll push that metric on this unit disk. Yeah. Okay. So this T, it maps this upper half plane to this unit disk. And if I take this W to be equal to UTZ and do all these computations, okay. So yeah, so do all this computations. So this I'm not doing this, you can see. So what turns out that so 4D so W is equal to UTZ. So 4W dW bar divided by 1 minus W square whole square. So this is equal to your dz bar by imaginary part of Z square. Okay, so this will get, and so this is the Riemannian metric on this upper half plane. Okay, so if I push the Riemannian metric of this upper half plane to your disk, so it will get this metric. Okay, so now so equip this this open disk with this Riemannian metric. Okay, so once you put this metric on this unit disk, so automatically, so what we have done, so what we have shown that this map T from this upward half plane to this disk, so this is an isometric. Okay, and it will also preserve angle because it is confirmed. This is just a Mobius transformation, so it is confirmed, so it preserves angle. Fine. Okay. Hold. So again, by this property of this Mobius transformation, so any Mobius transformation, it gives the set of circles and straight lines invariant. Okay. Yeah. So now, what are the geodesics in this Poincaré disk? Yeah. So geodesics in the sorry, I have not shared what you mean by Poincaré disk. So this unit disk with this hyperbolic, so this metric, so this will be called to be the Poincaré disk. So this will be called to be by Poincaré disk. Okay. Yeah. So now we have this upper half plane, and we have this this Poincaré disk, and now we know that we know the geodesics of this upper half plane, right? And yeah, so you note that this T of I, so this is equal to your 0. Yeah, so this vertical line here, so this blue vertical line here, okay, so this will go to, so this diameter. Okay, so this proves that this is a geodesic. Okay, and so this red line, so this is a geodesic here in upper half plane. So image of that, again, it will be a diameter. So this, again, it will be a geodesic. Okay, and this semicircle, so image of that. Yeah, so first of all, another observation is that, so why the image of, so let us call this to be my L. So why this image of this TL, so it is the diameter. Can anyone say this thing? So why the image of TL, it is the straight line, first of all. Why it is not a circle? So T of L, it will lie in the disk, right? So why it is a straight line? Why it is not a part of a circle? Yes, anyone?
One end of this line will map to the diameter, that is the 0 point will map to all the diameter, and the infinity will map that diameter to the opposite point. That's all.
I'm not getting what you're saying.
I'm saying that the 0 point, that 0 in the C. So 0 is mapped on the boundary.
Okay, T of I is equal to 0.
Yeah.
T of I is equal to 0.
No,
so
I'm saying T of 0.
T of 0. Okay, T of 0
will map to -1, right?
-1, correct. This one.
And T of infinity.
Correct.
We don't have infinity here. So
this will map to 1, right? Okay,
yeah,
good.
Map to 1. So
okay, all right. So you got this answer. And
I know that Mobius transformation preserves lines and circles.
Correct.
Lines will be mapped to either a circle or a line.
Okay, good. So this part is okay. This part is okay. And you can give a similar argument for this red geodesic also. Now the question is about this green geodesic in this upper half plane. So this is geodesic in the upper half plane. So let us call it to be L. So why TL is not just a line like this. It can be possible, right? T of L is just a line.
First of all, T of L won't pass through my I, right?
Yes.
I mean,
Well,
T of L doesn't passes through I.
correct. Yeah.
So T
Right.
of L doesn't passes through 0.
Through 0.
And
Correct.
it should meet the boundary perpendicular. So
yes. So that is one point. Yes. So this T of L. So yeah. So first of all, so T of R. So you should check this thing. So T of R in infinity. So this is exactly equal to the circle. Okay. So L is intersecting this R orthogonally, right? So L is intersecting this R orthogonally. So TL will intersect S1 orthogonally. So the image of this L under T, it has to be this thing, right? So it should meet orthogonally. So you know that T of L, it is either a straight line or a circle. If it is a straight line, it will not intersect the S1 orthogonally. So T of L it has to be a circle. Okay. All right. Okay. So therefore, what we have proved that geodesics. So geodesics in this Poincare disk. Okay. So it are either diameters or circular arcs which meets the circle S1 orthogonal. Okay. So these are my geodesics. So again, so you know the isometry. So PSL to R. So it is a subgroup of isometry of this upper half plane. Okay. So you can make from this using this T, you can show that the image. I mean this PSL to R, it will go here. So this PSU11. So this I have defined it here. So this will be the and subgroup of isometry of this Poincare disk. Okay, all right. So this I'll commit later. So this distance thing. All right. Maybe. So any doubt? Okay. So then let us move to this thing. So this I think I have stated once when I was saying about that is in the overview I have said this distance function. Okay. So how do you get an explicit formula for this hyperbolic distance? Okay, so let us take 2 points Z and W in this upper half plane. Okay, so what we are going to prove that, so this distance between Z and W, it is given by this formula. Fine. So already we have checked this thing. So if I put Z equals to IA and W is equal to IB, so if I just take the right hand side, so what you will get? So from the right hand side, what you will get, please tell me. So log of what? So I'll take A less than B. Let us take A less than B. So are you getting log B by A? Yes.
yes, yes.
So I'm getting the right hand side to be log B by A, right? And already we have checked this thing, right? So distance between, so if I take this two IA and IB, so this 2 points. So this distance, so this is already log B by A. So this formula is proven for this points on the imaginary axis, right? Okay. Yeah. So now, so what we are going to do it for general points. Okay, so what is the idea behind it? So let us take 2 points, any 2 points, Z and W, in this upper half plane. Yeah. So the idea is to find an element of this PSL to R, okay, which will take this geodesic C to your imaginary axis. Okay, so yeah, yeah. So if this geodesic it meets the real line at X and Y, and you define T of U to be this thing, so you can check that this T belongs to your PSL to R. Okay, and T of C, in fact, it will be equal to your I. Okay, so this implies that this T of Z it will be some IA, right? So T of Z it will be equal to IA, and T of W it will be equal to IB for some B uh, to be a real number. Okay, and we can assume this. Let us assume this A to be less than B. Okay, so are all of you with me? So I have taken 2 points Z and W. I have taken a geodesic C passing through Z and W, and the C is intersecting this R at X and Y, and I have defined this map T. So this T it belongs to your PSL to R, and yeah. So T of X is equal to 0, and T of Y is infinity. So this will say that this T of C is equal to your this imaginary axis. So this I is this imaginary axis. So therefore, this T of Z it will be equal to IA, and T of W is equal to IB for some A and B. And we assume this A to be less than B. Okay. So now we'll use this fact that this Mobius transformation it preserves the cross ratio. Okay. So what is the definition of cross ratio? So this you can yeah. So this is defined in compressed analysis. So this is the definition of this cross ratio. Okay, so you know this fact that if I take any Mobius transformation, so it preserves this cross ratio. Okay, so this means that so the cross ratio is denoted like this. So it preserves this cross ratio. Okay, okay. So now what you do? So you take this 4 points Z, Z bar, W, W bar, and take the cross ratio corresponding to these 4 points. So this T it is a Mobius transformation, so it will preserve this cross ratio. Okay, so this will preserve the cross ratio, and from the definition of the cross ratio, so we have this thing. Okay, so note that this TZ, so this is equal to your IA, and T of W is equal to your IB. Okay, sorry, excuse me. Okay, so now you do again this computation. So all this computation you make, and from this, so now what you'll get, so log of this thing, so this will be equal to your log of B by A. Okay, okay, and this right hand side, so this is exactly the distance between IA and IB. Okay, and now as T is an isometric, so T is so this is an isometric. So therefore, so T will preserve the this distance, right? Distance between Z and W. So distance between Z and W will be equal to your distance between TZ and TW. And so TZ is equal to your IA and TW is equal to IB. And this is nothing but distance between this IA and IB. And so this is exactly equal to this thing. Okay, so this distance is equal to this thing, log of this thing. So therefore we have this formula. Okay, so you have to apply this trick of this cross ratio to prove this formula. Okay, yeah. So once you have this formula in the upper half plane, And you know there exists an isometry, namely z goes to z minus I by z plus I, which takes this upper half plane to your this Poincare disk, and correspondingly to the Poincare disk also will get a formula. Okay, all right. So I think I am done with this distance thing. Yeah, so any doubt, please ask me. Okay. Maybe should I do this thing? Okay, so this that part I'll do it, right? Yeah. So as I promised that I'll be going to this to prove that this triangles are slim in this hyperbolic plane. So before that, so let me describe what you mean by Horo disk and this Horo cycles. Okay. Yeah. So first, let us take a point x belongs to your R. Okay, so one thing I want to mention here. So let us take this upper half plane. Okay, so this is my upper half plane, and we have this hyperbolic metric here. Okay, so now if I fix a point, so let us fix a point here. Let us call it to be P, and this is my R. So what will be the, I mean, this distance? So what will be, so this distance from P to your R in this hyperbolic metric. Is it finite? Is it infinite?
Infinite.
Yeah. So this will be infinite. So yeah. So this distance. So this is in fact infinite. Okay. So this R union infinity. Okay. So this is something you can say like this. So this is boundary at infinity of this. So there are too many infinities. Boundary at infinity of this upper half plane. Okay, so corresponding, so if you go upward, so we'll get a, okay, so this infinity is corresponds to your this 1-point compactification of the C. So if we go upward, so that distance, so if you fix this point, for example, if I take this P to be equal to your I, okay, and if I take any point IT, so distance between I and IT, so let us take T to be greater than 1. So this is your log T, right? And this goes to infinity as T tends to infinity. Okay, and if I take this T to be less than 1, so this distance, so this will be your this minus log T. This will go to infinity as T tends to 0. Is it okay? Okay, so therefore this R union infinity is something at infinity. Although the Euclidean distance from I to R it is finite. Okay, all right. Oh, sorry. Okay, so I want to describe what do you mean by this Horo disk and this Horo cycles. Okay, so first let us take this upper half plane, and you take a point X in R, okay, and you draw a circle, okay, so which is tangent to this R and tangent at the point X. So it is meeting this R only at X. So this object, so this will be called to be Horo cycle based at X. Okay, and this inside part. So just note that this point X, this is at infinity. Okay, so from the Euclidean world, we are saying this thing, and this interior part. So this I'll call it to be my Horo disk. Okay, fine. Yeah. Okay, so yeah, so now corresponding to infinity. So this I have this. So this is the Horo disk based at X belongs to you R. All right. And now if I take X to be your infinity, so what do you mean by Horo cycle based at infinity? So again, you take this upper half plane and you take any horizontal line. Okay, so let us take any horizontal line. So this Z equals to A. So this is my Horo cycle based at infinity, and this above part here. So this is I'll call it to be Horo disk based at infinity. Okay. So maybe I'll probably. Okay. So let me just say this thing. So so can you hear me?
Yes.
Okay. Okay. All right. Good. So there's a Horo cycle based at point X. Fine. So if I take this transformation, so X belongs to your R, right? So if I take this transformation, so is T is an isometry? What do you think? Is T is an isometry?
Yes.
Yeah. So yeah. So So here, so what matrix you will get here? 0, 1, -1, -6, right? So this belongs to your SL2R, right? So this T, it will correspond to this matrix. So this T is an isometry of this upper half plane. And what is the dynamic of this isometry? So, okay, so let me ask you this question. So suppose the C is the hollow cycle based at X. So where this T of C it will go? So this will be equal to what? Yeah, any answer? So T of C it will be equal to what?
So basically, it is inverting x to infinity, right? It's sending x to infinity.
Correct. Yes.
So it will send the Horo cycle to a straight line parallel to the.
Correct. So the image of this TC. So the image of this C under T. So this will be a straight line parallel to this x-axis, right? So this is so the T of C. So this will be a hollow cycle based at infinity. Okay, and also you can check that. So this interior part, this part, it will go to the part above this this horizontal. Okay, so T of C. So it will be hollow cycle based at infinity. Okay, okay, all right. So this is the definition of this hollow cycle disk. Now you can observe this thing. Okay, so maybe I'll not. Uh, okay. So now you take this hollow disk. Sorry. Okay. So now you take the hollow disk, some hollow disk based at infinity. Yeah. So this is my upper half plane. So this is my upper half plane. And so this is the hollow cycle based at infinity. And okay, and now if I take the hollow disk based at infinity, and now what I'll do, so I'll take two vertical lines. Okay. So let us take to this two vertical lines, and call it to be, so this point you call it to be your Z, and this point you call it to be by W. Okay, so now you can compute the length of this part, and now you go some t distance above, and let us call to this point to be my ZT, and this point to be my WT. Okay, so what you can show that, so this distance, okay, so the distance between ZT and WT, so it in fact it goes to 0 as t tends to infinity. Okay, so this you can show it explicitly, maybe in the tutorial time you can do it. So this distance it goes to 0. Okay, so if I take any two vertical axis into vertical axis, and so this distance, so this goes to 0 as t tends to infinity. Okay, so now if I draw the same picture for a hollow cycle based at some real number, okay, So again, note that here in the above case, so this angle is 90 degree. Okay, so this angle is 90 degree. Okay, all right. So if I do the same picture here, so this, yeah, so this horocycle will be like this. So this is based at the point X. And what will be this vertical line? So the image of, so the vertical lines are geodesics here, right? So image will be again geodesic here. And those geodesics will be intersecting the horocycle orthogonal, right? So we have this picture here. So, okay, yeah. So this is actually, so I have defined this T map here. So you can just put T inverse here. So yeah, so image of this vertical axis. So this will be something like this. Yeah. So all this blue geodesics. Okay. So these are infinite geodesics. So this will be so these are asymptotic to each other. Okay. All right. Any doubt? Okay. All right. So now, so we want to prove that the triangles in this hyperbolic plane are slim. Okay, so we want to prove that thing. And so before going to this proof, so let me define formally. So what do you mean by slim triangles, and what do you mean by thin triangles? Okay, so after that I can go to this proof. Okay, so I'll define this the slim triangles and thin triangles in general
Hello, sir.
geodesic metric space. Yes.
Sir, there is a question.
Sir, okay. So if T is an isometry, then horocycle always map to horocycle. Yes, correct. If so, how to show that? Okay, so that is the thing, right? So, okay. Yeah. So if I take X here, and if I take a horocycle here, okay, so this is my horocycle. Now, if I take T to be an isometry, or let us take T to be, so T belongs to your TSL to R. So you know that T of this R union infinity is equal to your R union infinity. All right. So T of X, either it will be infinity or again it will be a point here. So if it is infinity, already I have shown. So if it is not infinity, so T of X, it belongs to your R. So yeah, so this T of C, so this angle is what? So this is tangent, right? And T of C again, so T is a Mobius transformation, it will be again a circle. So it has to be something like this. T of C, again it will be a circle. So my picture is little bad. So this will be again my T of C. So T is a Mobius transformation and T is conformal. So this two things you have to use. Is it okay? Are you convinced? So if T of X is equal to your infinity, so then already you have shown. Okay, thank you. Okay, so now we want to define the slim and slim properties and thin properties for a general metric space. Okay. 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 So first, let me define what you mean by geodesic metric space. So I'll be coming why I have taken this definition. You start with a metric space. So let X be a metric space. So a map from, so let us take 2 points X and Y belongs to your X. Okay, and you take this closed interval. So a map alpha from this closed interval to this space X is said to be geodesic if alpha of 0 is equal to X, alpha of dxy is equal to Y, and d of alpha s alpha t is equal to your mod of x minus t, where s and t, it belongs to this closed interval. Okay, so this is my definition of geodesic. In upper half plane, I have defined something else. So length minimizing paths are called geodesics. And so now what is the relation between these two things? Okay. Okay. So I can, so this also Sri Krishna has defined length. What do you mean by length in this upper half plane? This metric length. So that thing I can do it the same for the general metric space. Okay. So first, okay, so I want to define length. So alpha be a path. Path means continuous. So it is a continuous map from this closed interval 0, 1 to this X. You know, metric space xt. So I want to define the length of this path alpha. Okay, so how do I define this length? So length of alpha, so this is defined to be the supremum over this summation t alpha ti minus 1 alpha ti. Okay, so where the supremum is taken over all partitions, so all partitions admitted like this of this closed interval 0. Okay, so this is my definition of this length for a in a general metric space, right? So now the question is that this length, it can be infinite also. Okay, so for example, if I take this path, so let us take R2 with Euclidean metric. So if I take this path alpha t, so t, so t, let us take t belongs to you and equals to 0, t equals to 0. Okay, so one can show that, so length of this path, okay, so length of this path, so this is infinite. Okay, and there's something called rectifiable path. So what is the meaning of this? So a path alpha is called rectifiable. So if length of alpha is finite. Okay, so I'll be always interested in this rectifiable paths. Okay, but so this is my definition of this length of the path. And now, so the definition of geodesic, it is given to be, so X is a metric space, and let us take 2 points. So So length, sorry, definition is given to be from this interval to your x. So alpha of 0 is your x, and alpha of dxy is equal to y. Okay, and this condition is given. For S. Okay. All right. So, so is this equivalent to saying this thing? So length of, so this alpha, so this is equal to your distance between x and y. Okay. So this is exercise. So this you can try. It's very simple exercise. Yeah. Okay. So now let us come to this thing. So this definition is equivalent. So this definition of geodesic, it is equivalent to this length minimizing path. So if you are unable to do this thing, so you can do it in tutorial. Okay. So a metric space. So a metric space is called geodesic metric space. So if every 2 points can be connected by a geodesic. All right. Okay. So now let me. Okay. So what are the example of geodesic metric spaces? So the upward half plane with this Poincare metric, this hyperbolic metric. So it is a geodesic metric space. If you take R2, the Euclidean metric, it's a geodesic metric space, and you can get plenty of. Okay. So what do you mean by slim triangles? So this already Sri Krishna mentioned. So let us take delta to be a non-negative number. So a triangle delta xyz in a metric space is said to be delta slim. Okay, so if each side of this triangle is contained in the closed delta neighborhood of other two sides of the triangle xyz. Okay, so this is same thing as what I'm saying. So what he said.
So is there a reason you're taking closed?
Yeah, so yeah. So close neighborhood I am taking because if I take a tree, okay, so 0, so delta will be 0 in this case, right?
Okay, okay.
Okay, yeah, I'll be coming to that. Okay. So if I take, so x, y, z, so these 3 points, so these 3 points, so this will give you a triangle. So in general, a triangle can be very bad looking kind of thing. So this is say geodesic joining x and y, and geodesic joining y and z. It may intersect the other geodesic. So this is a geodesic triangle. Okay, all right. So now, so what is the meaning of delta slim? Okay, yeah. So any question? So all of you got the definition of the slim triangle? Okay. So now let me give you this exercise. So let us take a tree. So let T be an infinite tree with edge length 1, or you can take this, or edges are isometric to the unit interval. Okay. So then, okay, so my picture is something like this. Yeah. So this is a tree. Okay. So this tree, it is a metric space that all of you believe, right? So I can assign a metric here, natural metric here. So for example, if I take 2 points here, let us take these 2 points here, x to y. Okay. So what I'll do, so there will be a vertex which will be very close to this x. I'll take this thing. So this length I know, so this will be some t. This length is 1, this length is 1, and this from this vertex to this thing, so this will be so from this vertex to this point, so this will be some s. So the distance here will be t plus 1 plus s, right? Okay, so it will be a naturally it will be a metric space. Okay, so is it a, so are all the triangles slim here? That is the question. What do you think? Are all the triangles slim here? So first of all, so if I take a triangle, how does it look? Okay, so let us take, this is to be my x, this is my y, and this point is my z. Okay, so what will be this triangle? How does it look? So what will be the geodesic joining x and y? So what will be the geodesic joining x and y? This is this thing, right? So this blue one, so this will be geodesic joining this x and y. Okay, and what will be the geodesic joining this x and z? So this, let us draw with this green color. So some portion of this geodesic joining x and z will overlap with this blue geodesic. Okay, so this green one, so this will be the geodesic joining x and z. Okay, and so what will be the geodesic joining this y and z? So what will be the geodesic joining and y and z? So this will be this thing. Okay, so the triangle, so the triangle is something like this. So you have a common vertex here for all these three sides. So the triangle is something like this. So this point is my x, this is my y, and this is my z. Okay, so on this part you will get, yeah, so these are the vertices here. So this is my w. Okay, so the triangle here, it is this tripod, will be this tripod. Okay, so this triangle, so this x, so note that, so this xz, okay, so this is contained in union of this xy and yz. Fine. So xz is contained in this union. Okay. All right. Okay. So this means that, and the same thing holds for the other sides also. So this means that the triangle triangle XYZ. So triangle XYZ. So this is my zero slim. Okay. Any doubt? So this delta. So this delta. And the definition of slim triangle. So this delta is equal to 0 for the tree. Okay. So this. So all the triangles in a tree are zero slim. Or okay. So there is another concept of this called thin triangles. So let me say what you mean by thin triangles. So let us again start with delta greater than equals to 0. So a triangle delta XYZ is said to be delta thin. So if there exist these 3 points CX, CY, CZ in the respective sides. So CX belongs to your YZ, CY belongs to your ZX, and CZ belongs to your XY. Such that this conditions hold. So I'll draw a diagram for it. Such that distance of X to CY is equal to distance of X to CZ. Distance of Y to CX is equal to your distance of Y to CZ, and distance of Z to CX is equal to distance of Z to CY. Okay. And if I take Y2 belongs to your XCY and Z2 belongs to your XCZ, such that distance of X to YT and X to ZT are same, so then, so this distance between YT and ZT, it is at most delta. And the same thing holds for the other sides also. So let me explain it with a diagram. Okay. Somehow my pens. So delta I have taken to be greater than equals to 0. So what do you mean by delta thin triangle? Okay. So let us take, so delta XYZ. Let us take this triangle. Okay. So this is my triangle. Okay. So first observation is that, so always you'll get a point CX. So you can split this triangle in this way. So always you'll get this point CX, CZ, CY, such that, so this distance between Z to CY is same as distance between Z to CX. So distance between Z to CY is same as distance between Z to CX. So distance between X to CZ is same as distance between X to CY. And distance between Y to CX is same as distance between Y to CZ. So this you have seen in this for the Euclidean triangle. So this, so you know the concept of this in center, right? So I take the in center and in radius, I draw the circle. The circle will touch all the sides in the CX, CY, CZ for the Euclidean triangle. Okay. So there exist CX, CY, CZ such that the following holds. Okay, first you have to check this thing. Okay. So now, so this is true for all the triangles. So now, so this triangle delta XYZ is said to be delta thin. So if I take any point here, so this, let us call it to be my so what I have to notate. So, yeah. So let us take a point ZT here, and let us take a point YT here in this geodesic, such that so distance of XZT is same as distance of XYT. So this T you can, yeah, so you can take to be equal to T. So this ZT, it lies between X and CZ. It lies here, and YT, it lies here. Such that this two distances, so this two distance from X to ZT and distance from X to YT, so these are same. So this is delta thin. So if this distance, so this is less than equals to delta. If for this thing, distance from YT and ZT, so this is less than equals to delta. Okay, and same thing is true for the other sides also. So if I pick any point here and pick any point here, such that these two distances are same, so this will be less than equals to delta. Yeah, so same is true here. So if these two distances are same, so this will be less than equals to delta. Okay? So this implies that, so this will imply that, so distance between Cx, Cy, this is less than equals to delta. Distance between Cy, Cz, so this is less than equals to delta. Distance between Cz and Cx, so this is at most delta. Okay, so this is the definition of thinness of it. So again, you can check that the triangles in your trees, so these are zero thin. Okay. Okay, so I'll stop here. Maybe it's a good idea to prove the slimness and thinness of triangles of the Poincare disk in the next class.